Today we will look at what the second derivative tells us about the graph of f of x. And what we're going to do first is look at the relation between the function and the first derivative. So let's remember that if f of x is increasing, the first derivative is positive, and if f of x is decreasing, the first derivative is negative. So that's the relation. F prime positive, f increasing, f prime negative, f decreasing. Now, the second derivative is the derivative of the first derivative, which means that if f prime is increasing, f double prime is positive, and if f prime is decreasing, f double prime is negative. So to understand what f double prime is telling us about f, we need to understand what f prime increasing tells us about f. So if we look at this picture here, here is a picture of f prime increasing. F prime is the slope of the tangent. Here it's a relatively large negative number, smaller negative number. 0 is becoming positive. As we move this way, those slopes increase. And what you can see is that the graph of the function bends up. So if f prime is increasing, the graph of f bends up. And the technical term we're going to use for this is that f of x is concave up. Thus, f of x is concave up exactly when f prime is increasing. Now, what about f prime decreasing? Well, here's a picture. Positive, less positive, 0, negative. So here's a picture of a graph where f prime, the slope of the tangents, decrease. And what you can see is that this graph bends down. We use that same language. We say f of x is concave down, and f of x is concave down exactly when f prime is decreasing. And now when we go up here and combine them, we get the following. F of x is concave up exactly when f prime is increasing, exactly when f double prime is positive. And f of x is concave down when f prime is decreasing, exactly when f double prime is negative. So reading here, f double prime positive, concave up, f double prime negative, concave down. So here's a definition. Suppose f is continuous at x equals c. F of c is an inflection point if the concavity of f changes across c. So in other words, on one side of c, this thing is either concave up or concave down, and on the other side it's switched. So concave up to concave down, or concave down to concave up, that point is an inflection point. And what this means is that f double prime changes sign. And if you think about what that means, f double prime changing from positive to negative means that f prime is changing from increasing to decreasing, which makes it a local extrema. And as a result, either f double prime of c is 0, or f double prime of c does not exist when you're at an inflection point. So the places to look for inflection points are where the second derivative is 0 or where the second derivative does not exist, but you're not absolutely guaranteed to find them there, just in the same way that critical points aren't always local maxima or local minima. So let's take a look at an example. F of x is x cubed plus x. F prime, 3x squared plus 1. F double prime is 6x. And the only place that f double prime is 0 is at 0. If we look at the graph, this is the graph of y equals f of x. And you can see that we're concave down here, and we're concave up here. So this is what an inflection point looks like. This is y equals f prime of x. And what you can see is the location of the inflection point is exactly a local minimum for the first derivative. So x equals 0 is an inflection point, and it's a local minimum for the first derivative. We can use the second derivative to test whether critical points of the function are local maxima and local minima, and we do that using something called the second derivative test. And the way it works is follows. Suppose that we're at a point where the first derivative is 0. If the second derivative at that point is positive, we're at a local minimum. If the second derivative is negative, then we're at a local maximum. Now, the way to understand this test is to look at these sorts of pictures. Here's a picture of a place where the first derivative of our function is 0, horizontal tangent, and the second derivative is positive, which means concave up. Now, you can see that the critical point has to be at the very bottom here, so that makes it a local minimum. Now we go over here. Here's another horizontal tangent, f prime of c is 0. This time, however, we're concave down, which means that our critical point is at absolute top here, which makes that a local maximum. Now, an important point, if the second derivative is 0, or the second derivative doesn't exist, this test gives no information. So what we mean by no information is you have no idea what is going on there. It's not that you can conclude there isn't a max or a min, it's you don't know anything. So you will have to go back to use the first derivative test, which may be computationally more complicated, but will always give you the answer. So let's look at an example. F of x is x cubed minus 3x squared plus 2. First derivative is 3x squared minus 6x. We factor out a 3x and get 3x times x minus 2. And very clearly, the critical points are going to be at 0 and at 2. So what we're going to do is look at the second derivative, f double prime of x, which is 6x minus 6, and we're going to evaluate it at these locations of critical points. F prime of 0 is just minus 6. That's less than 0. That means concave down. That's this picture. We got a local maximum. F double prime of 2 is 12 minus 6, which is bigger than 0. Concave up, local minimum. Okay, now let's look at this function a little more. One of the things to notice here is there is an inflection point at x equals 1. So here's f prime, 6x minus 6. It's obviously 0 when x equals 1. So f double prime of 1 is 0. But now if you look at the behavior of f double prime, when x is bigger than 1, 6x minus 6 is positive. When x is less than 1, 6x minus 6 is negative. Negative concave down, positive concave up. That's a point of inflection because the concavity has changed. If we take a look at the entire graph, we can see what the picture looks like here. Here's that inflection point we just mentioned. We tested x equals 2 and discovered it was a local minimum. And we tested x equals 0 and we discovered that it was a local maximum. If we have a graph of y equals f prime of x, finding concavity and points of inflection is even easier. So let's remember that f is concave up when f double prime is positive, but that's f concave up, f prime increasing, f double prime positive. And since we've got a graph of f prime, the key idea here is that f of x is going to be concave up where this graph is increasing. And the same idea, f of x concave down where f prime of x is decreasing. So we're just going to look at this graph and read that information off. Okay, so we can see that we are decreasing until we get to minus 2. We are increasing until we get to 0. we are decreasing until we get to 2, and then we are increasing for the rest of the time. So going down, going up, going down, going up. Remember, decreasing f prime means concave down function, increasing concave up, decreasing concave down, increasing concave up. And you can see the intervals on which everybody is concave up and concave down. And what's important here is that's an inflection point because concavity changes. That's an inflection point because concavity changes. And that's an inflection point because concavity changes. And as we noted previously, these points of inflection are local extrema for f prime. -2 is a local min, 0 is a local max, and 2 is a local min. Now let's put together most of what we know to sketch the graph of a function. Okay, so f of x is going to be x to the fourth minus 4x cubed plus 16. We start by computing the derivative, 4x cubed minus 12x squared. 4x squared factors out, and we have 4x squared times x minus 3, and clearly our critical points are going to be at x equals 0 and x equals 3. These are the critical numbers. When we chart the first derivative, we notice that when x is bigger than 3, that's positive, the product is positive. When x is between 0 and 3, that's negative, that's positive, product is negative. And over here, when x is negative, x squared is positive, that's negative, this is negative. So when we chart the first derivative, we go down, we go down, we go up. So 0 is a critical point, but it's not a max or a min. 3 is a critical point, and there's a minimum there. Now we chart the second derivative. F double prime is 12x squared minus 24x. 12x factors out, and we've got 12x times x minus 2, and the places where the second derivative is 0 are 0 and 2. We're going to chart the second derivative, and when x is bigger than 2, that's positive, this is positive, plus. Between 2 and 0, that becomes negative, this is still positive, positive times negative is negative. And when x is less than 0, 12x is negative, that's negative, negative times negative is positive. And that corresponds to positive is concave up, negative is concave down, positive is concave up, and we've got inflection points at 0 and 2. Now, when we plot this graph, we can see that 0 is an important point because it's a critical point and an inflection point. 2 is an inflection point, and 3 is a critical point, which is a local minimum. So we want to put those on the graph. We compute the values. F of 0 is 16. F of 2 is 2 to the fourth minus 4 times 2 cubed plus 16. That works out to be 0. And f of 3 is 3 to the fourth minus 4 times 3 cubed plus 16, which is minus 11. So we start by putting those values on the graph. 0, 16, 2, 0, and 3 minus 11. Now, in this region, if we look, when x is less than 0, we are decreasing and concave up. And that means the graph has to look like this. Now, why did it flatten off here? Because 0 is a critical point. There's a horizontal tangent here. Now, in this next region, between 0 and 2, our function is still decreasing, but it has changed the concave down. So our graph is going to have to look like this because it connects up there. Between 2 and 3, we've switched to concave up, but we're still decreasing. So our graph is going to have to look like this. And then finally, past 3, we're increasing and concave up, which means we look like that. And now if you look at this, you can see what every point is. This is an inflection point, which is also a critical point. This is just a standard inflection point, and that's a local minimum.